Okay, so good morning. We will start the class now. So I will start sharing the screen. So yesterday we had started the annotation of how a read basically happens in case of the Hadoop system, right? And we were following a sequence of read operation for an fread file, right? So this is what we were doing in the last class, right? I said there are a sequence of operations that you are supposed to perform before the read basically happens, right? Looking at the diagram, you can see that there is a HDFS client which basically makes a request for the opening the file. The distributed file system basically gets the addresses of these data nodes where the file blocks are allocated and where they are basically saved. Then HDFS client basically initiates a read operation. Now this read operation, which is initiated through this class FS data input stream, right, places the read request onto those particular nodes where the addresses are being given by the name node. Right after the reading is completed, the client basically closes that particular channel. Right. So this is something that we had in the last class. Right. And you can also see that an elaborate step where we are trying to get the addresses, where we are trying to find out where is the data node which is closest to that particular client node, where the data blocks are located. So these are something which we were basically trying to do in the last class, right? And also very important thing is whenever the file streams are completed with the reading and other things, you should basically close it with the close call, right? So the same thing we do in case of the C programming aspect also, right? We have a fclose of FP system call where we are going to close that particular stream input data which we had opened, right? So these are the elaborate steps, right? Now, if you look at the read related operations, what are the common aspects where a read related operations can get into an error? A read related operation can get into an error where the communication with the data node has failed, or there are communication latencies, or there is a readout time period which has elapsed and you're still not got the reading aspect of it. So these are some of the cases where the read can basically fail, right? And the data nodes may try to put that particular blocks of data which was allocated to them to another place, right? And the location of the addresses are not correct in that particular data node. So these are the cases where the failures can also happen. The other cases where the failures can happen is you are reading some particular file. So after you are reading some particular file, you find that there is a checksum error. That is, the amount of data that was originally hosted in that particular data node is not the same as the amount of data which was transferred to that particular client, right? So there is a data node error, right? Now, when you get a data node error, it is basically the checksum error. That means that block of data that you have shifted from that particular data node to your client node has corrupted, right? During the transportation, there was some bits and bytes of it during the transmission line where it has got corrupted. So you have not got the entire data at all, right? So these are some of the cases where a read basically comes into error, right? If you go to your file system concepts, right, you can also note that in the file system concept, you also have a case wherein which the file is not at all opened, right? And you are trying to do a read from that particular file, right? So then you get an error. So these are some of the cases of errors of read operations when you do in case of normal file systems. Okay. So if you look at the network topology of Hadoop, right? The network topology of Hadoop is very rich, right? The reason is because um, you already have one of the important failure concepts, which is no single point of failure in um, no single point of failure in case of Hadoop, right? The reason is because the Hadoop network basically processes high volume of data, right? The volume is not somewhere in MBs or something. It is in GBs and TBs is what the system is basically trying to deal with. So with such kind of whatever that we are trying to deal with, you must have data processing nodes which are capable of consuming or processing high volumes of data, or the network at the backbone, whatever is a local network with which it is connected, should be in a position to consider this high volume of data and have optimality in terms of speed, optimization in terms of speed, lesser bandwidth in consumption, and good rate of data transfer, right? So when we are talking about very high capacity of data, which is, let's take an example of a Facebook data which is in petabytes of data, right? When you talk about petabytes of data, let's imagine that 1 petabyte of data has to be transferred from one data node to another data node. Imagine the amount of data transfer rate that network backbone is supposed to support. It is supposed to support a very huge bandwidth, right? That is the reason why when you talk about rack servers, the nodes within the rack servers are connected within a very special network fabric called as InfiniBand, right? InfiniBand is a network connectivity just like an Ethernet, where the speed of the InfiniBand is somewhere around 56 Gbps to 76 Gbps of speed, right? You know that our Ethernet, traditional Ethernet, whatever that we have, supports a merely somewhere around 1 Gbps of speed, right? Which is not sufficient for transferring files which are of very huge size, right? So it is very important that we do have a network which is having a very good bandwidth, right? So let us look at some of the aspects of bandwidth, right? So measuring the bandwidth in real time is really very difficult. It is not as easy as what we see, right? uh, Developing a case where in which your bandwidth is of so many Gbps or so many kinds of Mbps is very difficult to measure in case of a real-time scenario, right? Because the real-time scenario would have got lot of load into the system, and keeping the load off and trying to measure the actual bandwidth is slightly difficult, right? And it may not be as accurate as what that network fabric is basically trying to offer you, right? So Hadoop basically has a network which is basically a tree structured network, and the distance between any two nodes is the sum of their distances, right? You know that in many of the concepts that you have learned, the physical location of a data transfer is more important than where the data is actually located. If the physical location of the data servers is very closely related, that means to say that it is easier for doing a file transfer, right? Faster way of doing a file transfer. If I am trying to get a Google server, which is in almost all the countries today, the best way for me to connect to a Google server is one which is physically very near to me. Probably an Indian server which is located in Mumbai, rather than connecting to a Google server which is there in London, right? So physically, I am very close to Mumbai when compared with London, right? So this distance related aspects matters a lot in terms of the data transfer, whatever that we are trying to deal with, right? So this is a very important case study, right? And also you should know that there are data centers where the data center is distributed across geographic locations. They are not there at the same place, they are there at different places, right? What does a rack server basically, or what does a data center basically have? The data center basically has a, set of rack nodes, right? And these rack nodes have nodes processing it, right? It's a rack basically, right? The rack has multiple nodes mounted on it, right? And all the processes runs on these particular nodes, right? So if you see the example that I gave you in the information week, where COVID-19 research lab was set up, right, by IBM, right? You can see that IBM Summit rack servers were shown in that particular diagram. So that is basically a rack, right? And the idea of the bandwidth being available comes in these scenarios. What are those scenarios? the processes which are trying to do some kind of processing are available only in the same node. So when the processes are available in the same node, the rate of transfer of the data is easier. The another scenario which can coexist is that the processes are on different nodes of the same rack, right? So the network fabric interconnect connecting the nodes between them is the InfiniBand. So the processor sits on different nodes of the same rack. So here also there is a good possible case of a good transfer rate. Now you can come into the third scenario wherein which the nodes are in different racks of the same data center. Now this is a tricky scenario. The reason is because the racks may be connected with different kinds of network fabrics. It may be Ethernet, it may be InfiniBand. Usually what happens is the rack to rack communication happens with an Ethernet, right? Because they are not physically located in the same system, same rack. So they are usually connected with Ethernet. Within the rack communication is obviously InfiniBand, right? Because the InfiniBand switch and InfiniBand connectors are very, very costly. People do not prefer to have the InfiniBand connectivity or switch between the racks, right? Because Ethernet is a cheaper technology when compared with the InfiniBand. So the better thing is people would prefer to look at InfiniBand, prefer to look at Ethernet rather than the InfiniBand scenarios. So even in the Ethernet connectivity, the cabling that is being used in the Ethernet connectivity is the Cat6 cable, which is the coaxial couple cable, right? Which allows up to a speed of 1 Mbps or 1 Gbps or 1.5 Gbps is the speed that it allows. The fourth important scenario which you can basically come to is the case of the nodes being available in different data centers. Now, this is a situation of a grid, right? In a grid kind of a situation, you have data centers which are geographically distributed across the nation, right? Yeah, across a particular geography. It may be in the same country, it may be in different countries, right? For example, Europe has got Euro grid, right? India has got Indian grid, right? Australia has got its own grid. IBM has got Blue Jack, Jaguar as its grid, right? Similarly, there are grids which are there in different parts of the globe, which is used for doing the processing, where data centers are distributed across a geographical location and they do processing. Now here the connectivity still becomes weaker, right? The previous scenario was nodes in different tracks of the same data center where some connectivity was supposed to be there. But here this is a scenario where nodes are there in different data centers. So the connectivity between them may be a terrestrial communication, a non-terrestrial communication, a satellite communication, a wired connection, a optical fiber communication. It can be any kind of communications, right? So given this particular scenario, it is completely dependent on the physical connectivity of these data centers, right? Let's say that we have got two campuses now, right? One campus is BMS College of Engineering, which is there in Basungudi, and the other campus is BMS Institute of Technology and Management, which is there in Yelanka. Now let's say that we have a data node, a data center which is located in Basungudi campus. We have a data center which is already located in Yelanka campus. Now I need to connect these two campuses. What are the different ways of connecting them? One is a traditional internet way of communication, where the ISP gives you some amount of bandwidth for connecting these data centers, right? So they have static IPs for doing this connection. Now, if not, you have a dedicated line of communication between these two centers. That is, you have taken an optical cable from Basunguri till Lanka. This is again a costly method, and it gives up the cost to the management. So the best way of connectivity is through a ISP connection, where the bandwidth is completely dependent on what the ISP basically provides. Right? He may provide 400 Mbps of bandwidth or 500 Mbps of bandwidth. Looking at that particular bandwidth, you are supposed to stretch the data center connectivity. Right? This is how these four scenarios basically matter in case of data processing. right? So if we visually look into some of the examples or the notations, it may look something like this. Nodes are represented with N, racks are represented with R. The data centers are represented with D in this case, right? So the node is N1, rack is N1, D is N1. The representation here can be given as slash D1 slash R1 slash N1, right? It is data center 1, rack 1, node 1, right? That is the representation, right? So the notation of calculation of distances for the last four scenarios what we have discussed in the previous slide is something like this. The first scenario was the processes exist in the same node, right? So that is distance of d1 slash r1 slash n1, d1 slash r1 slash n1. So the distance of this is 0 because the processes are existing on the same node, right? The distance of a particular node, right? The processes are existed in two different nodes of the same rack server, right? So that is slash d1 slash r1 slash n1 comma slash d1 slash r1 slash n1, right? So now the distance between these two is there are two nodes that it has to basically jump away, right? So that means to say, so that means to say that you have two nodes which you are supposed to go from one node to another node, right? So the distance value for this is 2, right? So different nodes are on the same rack server, right? The third scenario, what you can basically see is you have four nodes. So in this case, the nodes between the different racks of the same data center. So you have uh, the racks which are separated from two. The nodes are separated by two racks, right? The nodes are separated by two racks. So the distance between these two racks is
Hello. Hello.
Tell Teju.
Please, sir is not there. We'll leave. Yeah.
If it comes,
What to do then? We have to wait for him now.
yeah.
Between. Hello, is my voice audible?
Yes, sir.
Now,
Okay, so what was the slide that I stopped? Example, we are just trying to calculate the distance between different nodes, right? So this example, you can see that the first scenario is the processes which are existed on the same nodes, right? So it is the rack, the data center is represented as D, the rack is represented as R, the nodes are represented as N, right? So data center 1, rack 1 and node 1, right? Data center 1, rack 1 and node 1. So this is a process which exists in the same data center, same rack. So the obviously the distance for this will be 0, right? So the distance for a process wherein which it is located in different nodes of the same rack, right? So the standard distance for this will be 2, right? And similarly, at the nodes on the different rack in the same data center, the distance for this will be 4, right? And the distance for nodes which are located in different data centers, the distance for this will be 6, right? So you can see that in this particular figure, there is a visualization which is given for it, right? So which shows how the data centers are located, right? Our first scenario is the processes which are there in the same rack, same node, right? So the distance for this is 0, right? The processes which are there on different nodes of the same rack, the distance is 2 for it. The processes which are there in different nodes and different rack, the distance for that is 4, right? The processes which are there in different data centers, right, which are geographically located in different locations, right? So the distance for this is 6. This is the highest distance. So any copying or any other operations with the files or any data copying operations happens, the locality of data reference becomes very important. Shorter the distance or the closer the physical distance for that particular node for doing the copy, easier for you to enhance the speed of data copying, right? So if you are copying it from a server which is there in Mumbai and server from London, right, the data copying will be at a faster rate from the Mumbai server rather than the London server, because Mumbai is physically very close to me when compared with London, right? So if you do a relative comparisons like that, so it is very near to me, so the packets will flow at a faster rate due to the connectivity, and you can see that the data is being copied at a faster rate. So in the previous example, we saw the example of file read operation, right? So now we are seeing the example of a file write operation, right? So the file write operation is a special example basically because you can see that the file write operation has certain steps that is to be done before the write operation begins, right? So what are these operations? The first operation is you are supposed to have this creation of this particular file, right? Without having the creation of this particular file, you may not be able to write anything on that particular file. The second case is the file is not allocated with any kinds of blocks until unless it does not encounter any kind of errors during the process of creation or any other IO related issues during the process file creation. If there are any such kind of errors, there is a exception called as IO exception that would be thrown at this particular case, right? So this is the case, right? So if there are no known files, right? If the file does not exist previously, right? In that particular namespace, it does not exist. Only then the files are allocated with the files are created, checking the permission of the client. If the client has appropriate permissions to create that particular file, right, permission is given to that particular client, then the file creation happens. The distributed file system basically returns this FS data output stream to the client, an object for the client, so that the client can start writing the data into that particular file, right? Now here you can see the case of um, the complete scenario of your example, right? So you have HDFS client, which basically initiates a create operation to the distributed file system. This create is populated to the name node, where the name node basically does a lot of verification with the namespace, whether the same file is created or not created, right? After this is done, the name node would basically return an object called as FS data output stream. Now, once when this data output stream is given, the HDFS client starts with doing a write operation, right? Once when this write operation is initiated with this object, you can see that there is a write packet which keeps coming to the nodes. Now this write packet gets populated, or there is a communication with pipelines of data nodes where the write gets populated to different data nodes where the blocks are allocated for it to do the write operation. Once when the entire operation is completed, the write would basically come with an acknowledgement, and this would be acknowledged to this particular data node, and this particular data node would acknowledge it back to the FS data output stream. So once when the acknowledgement is completed, is done, then the HDFS client basically initiates a close operation. Now, when the close operation is initiated, a signal to the name node is sent saying that there is a file operation completed. So that signal is sent to that particular name node. So after this is completed, the entire operations of file writing is completed in the HDFS system. So this is the anatomy of how a file write basically is performed in a HDFS system. So the elaboration of this, again, you can see that when the client starts writing the data into the DFS file output stream, there is something called as an internal queue that is created. Now this internal queue is called as data queue, right, where the packets are housed in this particular data queue so that it can go out of the data stream and go into the data nodes for writing, right? And name node also does one more important thing. The name node does two important jobs while writing the operation, while write operation is performed. One is it creates the new blocks of that particular file. It also creates the replicas of that particular blocks in another data center. So it is one write is a direct write operations from the client. The other write is a write operations from the name node where it creates the replica of that particular file, right? And the data nodes basically form a pipeline which you have seen in the last place where the first data node, it goes into a serial kind of a write fashion. It is not a parallel write fashion. So in a serial write fashion, the write gets populated to other data nodes which are connected to this particular data node, until unless it finds the appropriate place where the block is allocated for you to write that particular data. Right? Once when the data writing is completed, the acknowledgement is populated from the place where the write originates in that particular data node. It gets populated to different places until unless you see a particular place where the data is supposed to go through. Right? So this is how the file write anatomy basically works. So in this particular scenario, let's say the case of a scenario where the data node fails. So when a data node basically fails, the writing also fails, right? That is, the pipeline which is opened for the data to flow from one data node to another data node, it gets closed. So the stream of writing itself gets completely failed. So the current block of data, whatever is the block which is stored on the current data node, will have to be shifted to another place, right? When the failure basically happens. The failure may happen with the last node, right? The failure may happen with this particular node where the writing is happening. The failure may happen with this particular node, or the failure may happen with this particular node itself. So the failure can happen in any of the data nodes, right? So the failed data node has to be removed from the pipeline, and the remaining blocks have to be written onto the data nodes which are keeping with a good health, right? And the name node notices that the block is under replicated and arranges for further replication to be created on the other node, right? So this is the operation that you're supposed to perform for this particular scenario. Okay, so what is the next thing? The next thing is, after the client closes the system call, the data nodes, the pipelines are also closed, right? And then there's a signal called as complete signal which is generated, right? So the next topic which we are basically dealing with is how do you do replica placements, right? How replica strategy is worked out from the same node, right? So this replica strategy is something where the data is supposed to be located on a particular node, right? And this particular data which is located on this particular node has to be copied onto the other place in exactly the same shape of how it is, right? So it can be copied onto the same rack, it can be copied onto the different rack, different nodes. So usual convention what is used is the data for replication is copied onto a remote rack, right, which is there in that particular data center. So it is called as off-rack communication, off-rack replication, right? So the second replica is an off-rack replica. The third replica what is created of that particular file is placed on the same rack as the second one, but on a different different node in that particular rack, right? For example, it may look something like this, right? So this is the replicated node. The blue rectangle what you're seeing here is the replicated node which is shifted onto a different track, right? So this is the second replication what happens. Now after the second replication, there is another third replication which is done onto the same rack of a different node, right? So this is how the data replication is achieved in case of um, Hadoop replication, right? So this is a very good replication strategies, because this basically enhances the factor of reliability, right? This makes systems more reliable, right? You have single switch, you have multiple switch to traverse, right? You have switches which can on failure can help you with an auxiliary switch, right? You can have uniform block distribution across your cluster, right? So these are some of the very good strategies for replication, basically. So the last part of this HDFS system is the data integrity part of it. How do we ensure that the data is in a high integration? That client, whatever is the data that he or she writes, is in the same format as what it is being stored in the data nodes. Right? Remember that the storage happens in the data node. It doesn't happen in the name node. Right? So how data integrity is to be ensured? You should also ensure that there is no loss of data, either during the storage process or during the processing process. So you should ensure that there is no loss of data at all. So how do you basically ensure? You have to build certain mechanisms for data integrity. So the volumes of data that flows through the system is very large, right? And the way of detecting a corrupted data is only through this checksum principle, right? If the data is corrupted, then obviously the checksum which is associated with that particular data is not matching the original data, right? So because of this, you have got error, right? The commonly used error detection code is the checksum CRC checksum algorithm. The CRC 32-bit algorithm is used in case of HDFS. So HDFS has got a transparent way of doing this checksum, right? So you have checksums that are written into default reading data. The default size of this checksum is 512 bytes, right? Since we are using CRC 32 checksum, the checksum itself will be 4 byte long, right? 1 byte is 8 bits. 32 is represented in 4 bytes, right? The storage overhead that is required for storing these checksum is less than 1% of the total storage that is required, right? So who is responsible for verification? The data nodes are responsible for doing the verification of data, right? They are responsible for doing this verification of this intelligently makes aware of itself that there is a data loss or there is no data loss, and the replicas are very good or there are uncorrected replicas. So the system will make sure that the data is so this is data integrity is maintained in H. To talk are mounted on the top of ext file system, right? So the checksum and other things that is to be performed is performed by the local file system. Checksums are named .cr. That is the convention that is used for representing CRs. Okay, and you can also see that the database is controlled by IO this particular file, right? So whenever a file is the checksum will be understood. After reading also the checksum will be understood to match the checksum file. This is how the checksum is basically done, right? And checksum management or computation is fairly a very cheap job, right? Where so the applications which are represented with the uniform resource identifier, that is URI name, by setting the property of fs.file.impl, right? You can see that the file systems are obtained from this particular package, which has got this org.apache.hadoop.fs.raw local file system. So this is the file system that is used for doing this, right? So so some examples of configuration created. Then you have file is equal to raw, right? So if it is a job, the class is job configuration. If it is a normal aspect, it is just a configuration file that you are going to use in this particular case, right? So you can basically take a snap of this particular slide also, where you are trying to understand the initialization aspect of your file system. Okay. File system. So the checksum file system is something where the checksum is created with this particular case, right? File system is equal to new file of FS. Raw of FS is the object of the system. Right? Is the general idiom or general syntax which is used for a checksum file system. So if an error is detected by a checksum system, default implement local file system moves the offending file with the checksum on the same device, looking for these bad files and take an action on this particular bad files. Okay. So I will stop at this for today, right? So I will continue aspects in the next class, right? Before